Hi, everyone. The next topic is prospective and retrospective sampling. So we have, okay, so at first we define prospective sampling and retrospective sampling. So in the prospective sampling, the predictors are fixed and the outcome is observed. So we have the predictors. So that typically in an experiment that we control the input. For example, we control the temperature at 2 different levels, or food intake level to 2 different levels, or we give drug treatment group and we don't give the drug, the control group. So we set the predictors. Then we observe the outcomes. And in the retrospective sampling, the outcome is fixed. So retrospective, so that after something occurs, then we just the samples, just the malignant patients, and we sample some benign patients. Then we compare. So that is the retrospective sampling. And so these two methods have the pros and cons in practice. For example, the prospective sampling is good to identify the cause and the result, the relationship. For example, if we control the drug to give to the patients, then we can see whether or not the drug is useful. But it takes time, so sometimes retrospective sampling is good. So because already the outcome is available, so we can immediately analyze the data. And the logit function has some good properties that the interpretation of results through the odds ratio, to be exact, the log odds ratio, does not change between these two studies. Okay, so this is another example, the incidence of respiratory disease in infants. So we have the two groups of the babies, and the one group is the babies for the given bottle milk, and the other is the babies fed by the breast milk. So we have the number of babies here, and some babies got the disease after 1 year, and some other babies that don't get disease after 1 year. And you can see the proportions are different. So in terms of prospective sampling, if we focus on the difference between the bottle and the breast, actually the breast have less disease, 47 again, versus the non-disease is 447. So almost maybe a little less than 10%. But for the bottle, if the food is bottle, then that is 77 versus 381. So that is around maybe 20%, so more disease. So in this prospective setting, the log odds are 77 over 381. So this is a kind of p over 1 minus p. So log of 77 over 381, and the second group, the breast group, then that is the 47 over the 447. So the difference is the effect size. And retrospective sampling, so that is that we sample several babies from the disease group and some babies from the non-disease people, babies. Then actually we can see for the disease group, the more babies, relatively more babies are given the bottle milk. And the non-disease group relatively have get the breast milk. So that proportion in terms of log odds is the 77 over 47 and the 381 over 447. So the difference between these two numbers is the effect size. And you can see that for the first one and the second one, that we get the same effect size. So this quantity minus this quantity is the same as this quantity minus this quantity, because this quantity actually from the prospective study. So this is okay, log of 77 minus log of 381 minus log of 47, the plus the log of 447. So actually, if you expand the second term, actually it's the same. So we can see the same. So odds ratio is good to interpret in terms of a kind of interchangeability of the prospective sampling and retrospective sampling. And this kind of interpretation cannot be done if we use other modeling. So if we use the, for example, probit model, the log odds ratio does not make any meaning in that model. So logistic regression has another benefit here. Yeah, and one thing we have to be careful is that in retrospective study, often the individuals from one group, for example, the disease group, is more likely to be selected in the study. So we have a kind of sampling bias. So this affects the estimated estimated probability of disease, of course, because the more observations from the disease group, but does not affect the effect of the coefficients of predictors. Does not affect the coefficient of predictors. So actually, we have the parallel shift. So if we have sampled the more, disease babies with disease, then estimated probability gets higher, but the effect of the predictor that does not change in this model. We will see this. So at first, we define several quantities. The pi1 is the conditional probability of individual is included in the study, given that baby has disease. And pi naught is probability of the baby is included in the study, given that the baby does not have disease. So probability of study given non-disease. And P of X, this is unconditional probability of disease. So just for the entire world, how many babies have disease. That is the P of X. Then the P asterisk of X. So this is probability, excuse me, probability of disease given that baby is included in the study. Then using Bayes rule, that can be calculated pretty straightforwardly, because the P asterisk X is probability of study. This is the denominator, and the numerator is probability of the disease and study. Then further, we decompose this into the probability of disease and probability of study given disease. And the denominator, that we have two cases. The baby has disease and in the study, and the baby does not have disease and in the study. So the first one is the baby is in the study and has the disease. And the second one, excuse me, it does not have disease, that is 1 minus P of X probability, then that is included in the study. And if we think about the logit of the P asterisk X, so that is P asterisk over 1 minus P asterisk, then that becomes this shape. Because the 1 minus P asterisk is pretty simple shape, that is pi naught times 1 minus P over pi 1P plus pi naught 1 minus P. Because actually this and this are the same. So if 1 minus, then we got the other term, pi naught times 1 minus P. So if you take the ratio, the denominators cancel, and this just becomes the log of the pi1 over pi naught times the p over 1 minus p. So then we decompose it, then we can just get this the coefficient. So that means if you sample more babies from disease group, if pi1 is larger, then we have this parallel shift, the log of pi1 over pi naught. But just if we adjust this, then the other part is not affected. So we can actually calculate the p asterisk x based on the p of x and pi1 and pi naught. Okay, so this is section 4.3.